Section 29.3, we're going to talk about Bohr's model of the atom. Following Rutherford's discovery that the atom had a very small nucleus, about 1/100,000th the size of the atom, and it contained most of the mass of the atom, the natural thought was that perhaps the electrons orbit the nucleus much like the planets orbit the sun. And there was a major problem with this, and that is that it was already known that anytime you accelerate an electron, either you slow it down or speed it up or cause it to go around in circles, it radiates energy away from itself. It radiates electromagnetic radiation. And so if the electron is orbiting the nucleus, it was pretty quickly concluded that energy should be carried off by the emission of the electron as it accelerates in its circular motion around the nucleus, and yet all atoms seem to be stable. The problem with the emission is that the electron would lose all its energy and collapse into the nucleus. And this is a classical Newtonian way of looking at things, that the electron is a point particle going around in a circle, and therefore it should radiate. It was seen that electrons going around circles radiated, but it was electrons going around very large circles, like inside of a gas tube or a vacuum tube, where it was spinning in circulating in a magnetic field, for example. But those are macroscopic sizes, and on the microscopic size, when the electron is in the atom, we really don't know, they didn't know, what the proper way to describe it was. The natural inclination was to use Newtonian mechanics, where we have this idea of orbit, but a radically new way of thinking had to be made. And so Niels Bohr was the first to offer a new way of looking at the atom, and frankly, he had to make some sort of postulates or guesses about the atom in order to make advances in its understanding, which later on could be seen in better context. We now call it the Bohr model of the atom, and it represents an early stage of the development of quantum mechanics. So his idea was based on a few postulates, which are really the basis of science. You have to start with some assumptions in science. And the ones that he started with were famously made into postulates that are credited to him for advancing our understanding of the atom. One of the postulates, which may sound a little bit funny, because it was thought that electrons orbiting the nucleus would radiate and therefore lose their energy and collapse into the nucleus, he simply postulated that electrons stay in certain allowed orbits. It wasn't necessarily a Newtonian orbit, but he was basically aware of the fact that these electrons seem to be in stable states, and so he postulated that they are allowed in certain orbits. Only a few are allowed based on the specific characteristics of a particular atom or element, and these are called stationary states. So this was his first postulate. His second postulate was that they occupy certain levels that are associated with energies, that there are different levels that the electron could exist in, or orbits, that have specific energy. And so you see on the right side here a diagram that illustrates the possibility that the electrons can move from one of these stationary states to another. So the second postulate was simply that each stationary state has a discrete energy that are ordered. There is a ground state with the lowest energy, and then there are states above that we call excited states. And the point is that they're quantized and that they have specific energy. Now, if this is the case, then according to what we've seen in atomic spectroscopy, the atom can go through transitions. It can either, and we call them quantum jumps, it can either absorb a photon and get promoted to an excited state, as we see here in the bottom diagram, or it can, once it's in an excited state, it can emit a photon and collapse back down to the ground state. So these are the two possibilities that were understood once we have the basis of the atom consisting of discrete states with different energies. And so there's this absorption process and emission process. Now again, this is something that was understood by spectroscopists, but the mechanism by which the atom negotiates these, whatever the transitions are that give rise to these absorptions and emissions, were not known. And so Bohr was effectively postulating that the atom exists, that the electrons are stable, and that they occupy certain orbitals with certain energies. It also turns out that atoms can be bumped by thermal agitation and get promoted to excited states. So this is another non-optical means by which atoms were excited, and this was soon observed in the laboratory as a counterpart to the optical excitation and de-excitation. Now, when an atom is bumped into an excited state, it naturally collapses back down to the ground state by the emission of a photon, just as it does in the case where it's excited by the absorption of a photon. So there's really no difference once the atom's in its excited state. The way it gets to the ground state is simply by emitting a photon and making that transition. Okay, so the implications of his model are far-reaching. Now, keep in mind that this is a very early model of the atom, and quantum mechanics had not yet been developed. So the fact that he postulated that the electrons orbit in certain stable orbits and that they don't radiate away and collapse into the nucleus was basically an acknowledgement that this is the way nature works, and we might as well postulate it with the hopes that later on that postulate would then be understood as being the product of some underlying state or character of the atom that was yet to be discovered. So matter is stable. Once the atom is in its ground state, which is the very lowest energy state it can be in, it will remain there effectively forever. And that atoms emit and absorb a discrete spectrum, and the energy of the photon by energy conservation is exactly equal to the difference in energy between the two states, the final state usually being below the initial state if it's an emission, and the final state being above the initial state if it's an absorption. And the energy of the photon that's either emitted or absorbed must have the energy that corresponds to the difference in those states, and that's really a matter of energy conservation. And then we can also produce the emission spectrum by collisions, and there was a famous experiment done by Franck and Hertz that demonstrated this. They took mercury gas, and they were able to send electrons through that gas that would collide with the gas atoms and promote them to their excited states, and then when they collapsed back down to the ground state, there was a characteristic purple glow from the emission lines from mercury. So this was actually demonstrated in the laboratory, that you can excite atoms by collisions as well as absorption of photons. Okay, so his model then consisted of what we can depict by an energy diagram. You see in this diagram that there are transitions from the ground state on up, from the n=1 state to the n=2 or the n=3 state. And then once in those states, they can make transitions back to the ground state. If in the n=3 state, one of the transitions back to the ground state is the 3-to-2 state, and the other one is the 2-to-1 state, or 3-to-1 state. So there are two possible transitions downward from the n=3 state, whereas there's really only one way to populate the n=3 state, and that is straight from the ground state. The reason for that is because when an atom is in its excited state, say for example an atom is excited from the ground state to the n=2 state, once it's in that state, it decays very quickly back down to the ground state. And the possibility of it waiting long enough to then absorb another photon and be promoted to the n=3 state is simply beyond probability. It's in its n=2 state far too short. And so we don't see the n=2 to n=3 transition in the absorption spectrum, but we certainly see it in the emission spectrum, because there's nothing preventing the electron in making a transition to the ground state, either by going from n=3 to n=2 and then n=2 to n=1, or straight from the third state to the first state. Each element also has a unique spectrum, and it was recognized from spectroscopy that that was the case. And so what Bohr was able to conclude is that different elements with different numbers of electrons have, therefore, different stable orbits based on the fact that they have different size nucleus, different charge nucleus, different number of electrons. And so each atom was seen to be unique in that respect, and spectroscopy would help uncover those differences, and what physicists wanted to do was be able to explain why atoms have the particular states that they do, which later came with the advent of quantum mechanics. Okay, so this just summarizes what I just said. We can emit photons from excited states, we can absorb them from the ground state, but the absorption and emission spectra don't contain the same number of lines. The emission spectra usually contains more lines than the absorption spectrum because, again, the emission spectrum can, from an excited state, can take many paths down to the ground state, whereas the excitation to that state usually comes directly from the ground state. So here's an example where we have three states, a ground state with 0 electron volts. We automatically call it 0 electron volts because there is no state lower than it. even though there is something called quantum zero-point energy, which means the ground state has a finite energy associated with it, but since it's the lowest in the system, we label it as 0, and then all excited states relative to that ground state based on their energies. So here we have a system with a ground state and an n equals 2 state at 2 electron volts, and an n equals 3 state at 5 electron volts. So for the absorption spectrum, we have the possibility of going from the ground state to the second or third state, and the energy of the photon is exactly equal to the difference in the states that it makes a transition to and from. And so in this particular case, the frequency of the photon for the absorption spectrum from the ground state to the third state is 5 electron volts, because that's the difference in those two states. And that corresponds to a frequency of 1.2 times 10 to the 15 hertz, or a wavelength of 250 nanometers, which is just beyond the visible spectrum in the ultraviolet. And then the 1 to 2 transition has a longer wavelength. It's in the orange region of the spectrum, which can be easily seen. And then in the emission spectrum, we have 3 possibilities. We have the 5 electron volt to 2 electron volt transition, which is the 3 to 2 state. That has a wavelength of 410 nanometers. And then the subsequent 2 to 1 that would follow that transition is also in the visible spectrum, as we've just seen in the orange. And then there is also the 3 to 1 state, which is the reverse of the absorption spectrum 1 to 3 state, and that has the same 250 nanometer wavelength, which is in the ultraviolet. Okay, that takes care of this section. Now we'll move on to the next section.